Yeah, and then with the pep rally yesterday, I thought it was Friday. So,
Yeah, me too.
you
It
know,
feels like it's been like 2 weeks.
it does this week. Some sort of strange time warp. Okay, now let's go over these problems. Let's see if you and I share our um, answers. Make sure that we're on the same page. Now, this is not totally comprehensive. I realized after I was looking at this that I forgot to put some of those things about manipulating the equilibrium constant. Remember, like if you write the forward reaction and then you want the equilibrium constant for the backward reaction, you reciprocate it. We can go over that. Don't worry about it. We'll go over it. Some of these things are, like I said, not too bad. Okay, question number one. The trick with question number one, and all of these problems, not that it's a trick, but you have to be very careful because if I give you moles and liters, you have to get concentration in molarity. Molarity is moles divided by liters. So don't forget that. So in this first one, what I did here too is I went ahead and I said, well, what don't I need in my equilibrium constant? I don't need phosphorus pentachloride because it's listed here as a solid. So right up here, I just scratched that phosphorus pentachloride out so that you're not even tempted to put it in. Okay, so go ahead and do that. So when you go ahead then and solve for the concentrations, I'm just dividing moles by 3. My equilibrium constant for this reaction, K, is going to be equal to 0.166 times 0.25 squared divided by 0.0166. And so I get a number of 0.625 for my equilibrium constant, which is in that gray area. It's in that area where K is less than 10 and greater than 0.1. So it's kind of in that area where we sort of have equal amounts of reactant and product. If you're going to say anything, you might say it's slightly reactant favored based upon concentrations. Okay, Anna.
So you don't include the 0.7475 at all in your calculations at all in here?
What's in the parentheses after the PCl5?
Solid.
So we never include solids. We never include pure liquids. Okay, so get that in your mind. Now, this don't forget what K. This is Kc. This is based upon molarities. So if I'm just dealing with molarities, I have this value. Now, what about Kp? Kp is interesting because my delta N here is 2, and hopefully you can see that because we have 3 moles of gas on the product side, 2 moles of HCl and 1 mole of POCl3, and on the reactant side we have 1 mole of water. So 3 minus 1 is 2. So we have Kp is equal to 0.625 times R OA21. I'm going to leave the units off just for the sake of being lazy. Times 373 Kelvin raised to the second power. Okay, that's my delta N. When you do that, you get a value that's 586. Guys got that? Okay. Wow, that's a pretty big number compared to the 0.652 or 625 or whatever it was.
Kira Marbaker and Lola Dentech in the attendance office.
So that would indicate that this is reactant favored, or product favored, wouldn't it? That number. So here's a question that I posit to you, and maybe you can do some research between today and tomorrow. Why is Kp so much bigger than Kc? Well, yeah, mathematically we can say that, but chemically, physically, why do we have a bigger number? That might be a good question to ask. So that's it. That's that one. I think we did that one yesterday, or this one about ammonia many times. That's the one where you plug the numbers in, you get like 1.25 times 10 to the 7. So I'm not going to go through that one again.
So,
All right, Landon, what do you got?
remember how you were talking about that like box thing with like the moles in it and then like moving around? The product would have more because it has 1, 2, 3. And that one only has the H2O.
Yes, so because pressure has more effect on equilibrium than concentration. Yeah, you're right. You're right. Good, good, good.
I'm sorry. I had it in my head. And
Yeah.
I was just trying to
Yeah.
express it.
Yeah, because changes in pressure will have a much more of an effect. Good. You're thinking like a chemist. Okay, at 35 degrees C, the value of Kc is 1.6 times 10 to the negative 5. So, the reaction we have here is 2 NOCl in equilibrium with 2NO plus Cl2. This is an ice chart, by the way, ice chart problem. So we're going to go I, C, E. My initial concentration, once again, I give you 1 mole and 2 liter flask. So that's going to be a 0.5 molar solution. Well, it's not, these are all gases, so it's not really a solution. And then we have well, it is a solution because gases can form perfect solutions as well. So 0 of that and 0 of that. It's not an aqueous solution. So I'm going to have minus 2x because there's a 2 in front of my nitrosyl chloride plus 2x and x. And then my equilibrium concentrations will be 0.5 minus 2x and then 2x and 2x. So when you go ahead and plug your numbers in here, we're going to say K is equal to 2x, but I have to square it, times x over 0.5. Now, you could put the minus 2x in there and mess with the quadratic, but we're not going to do that. We're going to assume that 2x is small compared to that. So 0.5, but I have to square that too because there's 2 in front of that. And when I do that, you're going to get an x value of 0.01. When you solve this for x cubed is going to be 1 times 10 to the minus 6. Just take the cube root of both sides. You don't even need a calculator for that. It's just 1.01. So the way you write your answer for this, and this is very important, you write your answer this way because the question says, what are the equilibrium concentrations of all species in the flask? So you write the NO is going to be 0.02 molar because it's 2x. The Cl2 is going to be 0.01 molar. And the NOCl is approximately 0.48 molar, if you want to go back and put that number in there. Or if you just said approximately 0.5 molar, that's fine too, because we made that assumption. In this case, though, we probably, since 0.02 is not that small compared to that, we should go ahead and subtract it. Or just go ahead and use the quadratic if we want to be a bit masochistic. Next question is the same reaction. Shouldn't have erased that. We have the same reaction, and we're going to talk about Kp. So we're going to 2NOCl equilibrium with 2NO plus Cl2. Now, Kp is 4.5 times 10 to the minus 8 for this reaction at this given temperature at 240 degrees C. So, we know, let's say I, C, E, the initial partial pressure is 0.64, 0 and 0. Do it exactly the same way. 0.64 minus 2x, 2x, x, and again, same deal. 0.64 minus 2x, 2x, and x are my equilibrium concentrations. Same exact problem, except now we're using Kp. So don't forget, Kp is going to be the partial pressure of NO squared times the partial pressure of Cl2 divided by the partial pressure of NOCl squared. Do not put plus signs between things. These are all products, okay? So let's do it. Same old song and dance here. 4.5 times 10 to the minus 8 is going to be equal to 2x squared times x, or that whole quantity squared, times x divided by 0.64 minus x minus 2x squared. We're going to get rid of that minus 2x, and so then same deal here. We've got 4.5 times 10 to the minus 8 is 4x cubed divided by 0.64. So I didn't have a chance to plug that one, and we'll go with it. Let's see what we get. 4.5 times 10 to the negative 8 times 0.64 divided by 4. We'll take the cube root of that. And I get a value for x is 0.0019 atmospheres, as long as we're, yep, atmospheres. Remember, that's our pressure. So the way we would write the answer, are you not able to see with the computer there?
Are you supposed to scale the difference?
Oh, yes, yes, yes,
Because
yes. Yes, 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 thank you, thank you. Yes, that was an error on my part, so let's go ahead and take care of that business here. So 4.5 times 10 to the negative 8 times 0.64 squared. Now, I'm going to divide by 4 and take the cube root. And I get 0.0017. Does that match up with what you guys got? So, the way you report your answer, okay, they're asking for the equilibrium partial pressures and all of these things. So, the way you would go ahead and say this, I'm going to erase this here, is you would say the pressure of NO is going to be 0.0034. The pressure of Cl2 is going to be 0.0017 atmospheres, and the pressure of NOCl, we see here, is approximately 0.64 atmospheres. Or if you wanted to subtract that out, you could certainly go ahead and do that. 2x. Not going to make that much difference. All right. Now we have some Le Chatelier's principle questions. It says, suppose the following reaction has already reached equilibrium. I'm sorry, there's no arrow in there. So let me write the reaction. We have UO2 plus 4HF in equilibrium with UF4 plus 2H2O. And let's make sure we have this. This is a solid. This is a gas. Yeah, this is a gas. And this is a gas. So, predict the effect that each of the following changes has on the equilibrium position. tell whether the equilibrium will shift left, right, or will not shift. So, what happens now? First of all, let's write the expression for this. I'm just going to put K here. It doesn't matter if we talk about KP or KC. Let's talk about KP, I guess. And that's going to be the pressure of H2O squared times the pressure of UF4 divided by the partial pressure of HF raised to the fourth power. What is not included in this? Right, why? So is the addition or the removal of that going to affect anything? No. It's not in our equilibrium function. So if you add some more of that, it's not going to do anything. Now, what happens if the reaction is performed in a glass container? Hydrogen fluoride has a unique property of being able to attack glass. And have you ever seen glass that looks like kind of opaque or what's the word I'm looking for, frosted, like that? If you put hydrofluoric acid in a beaker or something like that, it'll attack that glass and it'll make it look frosted. So and that stuff is very dangerous. It's a very interesting chemical. Anyway, if this is put in a glass container and this is reacting with gas, essentially what's happening to the hydrogen fluoride? What's that? I mean, it's supposed to be reacting with that, but if some of it's being taken away because it's reacting with the gas, if this is being taken away, it's going to happen. It's going to shift back to try to replace some of that, right? It's going to try to reestablish that. Okay. What happens if you can somehow pull out the water vapor? Which way is it going to go? Good, toward the products. Yep, Le Chatelier's principle is not so bad. I think you guys will do really well on this. But I do want to make sure that you understand that manipulation of equilibrium constants as well. Oh, another one. I forgot my arrows here. I got CO gas plus H2O gas, and that's in equilibrium with H2 and CO2. Okay. What, gas. Which way is it going to shift if I can remove some CO2? Don't be afraid to shout it out. It goes that, yeah, it's going to go, if I'm taking out the CO2, it's going to shift in that direction. What happens if I add more H2O vapor? Add more stuff there. Yeah, wants to get rid of it. How about if I increase the pressure somehow? Maybe I change the size of the container, I put an inert gas in there, and I increase the pressure. What's going to happen, if anything? Nothing, right? How many moles of gas on this side? 2. Everyone's afraid to talk. How many moles of gas on that side? 2. So the equilibrium shifts when you change pressure only if you have different numbers of moles of gases on either side of the atom. This reaction happens to be exothermic. Delta H is negative. Exothermic. What does that mean? Does that mean heat is on this side or heat is on that side? Right. This gives off heat. It's exothermic. So what happens to this reaction if I'm carrying it out at a higher temperature? Which way is it going to go? Yeah. Remember, if this is giving off heat and I increase the temperature, it's going to shift back that way. Now, if I cooled the temperature, it would go in that direction. Okay. Once again, if your pressure is increased, same deal, nothing's going to happen. Okay. We have a little reaction here. CO gas plus 2 H2 gas in equilibrium with methanol gas. It says the reaction to prepare methanol from hydrogen and carbon monoxide, shown there, is exothermic. You have to know exothermic. Negative, that means heat. Over here, if you wanted to use this reaction to produce methanol commercially, would a high or low temperature favor a maximum yield? Explain your answer. I'm just going to call on someone. Jilly, what do you think? It's exothermic, and you want to carry out this reaction. So would you do it at a low temperature or a high temperature? What's that? High temperature? No. Well, yeah. Don't buy a lottery ticket tonight. You want to remove. You want to remove the heat, right? So what do we want to do? Yeah. Colin, what are you going to do? Low temperature or high temperature? Low. We want to get rid of that heat. So Chatelier's principle says we're going to push the reaction in the forward direction. It's okay.
So if you start at a low temperature in the reaction, you
Well, exothermic means that the reaction produces heat
yeah.
as a byproduct. So you want to remove that heat. So you might want to do this in an ice bath, for example.
Okay.
Okay. All right. This last one, I don't know if you want me to go through all of them. We could just go through one of them because they're all the same. It's Q. This is Q versus K. Okay. We have our reaction for ammonia. By now, you should be able to write this reaction by heart. We've been talking about this reaction forever. And so with the K value for this is going to be NH3 squared over N2 and H2Q. So they give you a value for K. K's value is 6.0 times 10 to the minus 2, okay, at 500 degrees C. You have to carry that reaction at a very high temperature. So it says predict for each of the following cases if the system is at equilibrium, and if not, will it shift? So let's just look at one of them. Let's look at A. Well, my Q value here, set up exactly the same way as K. My Q value is going to be 1.0 times 10 to the minus 3, and that's going to be squared. Oh, this is that same one that we looked at before, the same value. So 1.0 times 10 to the minus 5, and 2.0 times 10 to the minus 3, but that has to be cubed. And that's that one that came out to 1.25 times 10 to the minus 10 to the 7. Remember when we did that one before? So obviously Q is much greater than K. We've made too many products. It's going to shift back toward reactants. Let's do another one. Let's do them all. Why not? Okay. Situation number 2. I've got 2.0 times 10 to the minus 4 mole. I don't have to put that in there. And that's going to be squared. And I've got 1 times 10, I'm sorry, 1.5 times 10 to the minus 5. And over here we've got 3.54 times 10 to the minus 1. That has to be cubed. So this one we'll have to plug in. Anyone have a value for it? Anyone get one? Okay. 2 times 10 negative 4 squared is going to be 4 times 10 to the minus 8. And divide by 1.5. times 10 to the minus 5. And we'll divide that by 3.54 times 10 to the minus 1 cubed. And I get Q here is going to be 6.01 times 10 to the minus 2. So I say that my Q is close enough to my K to call this equilibrium. Matter of fact, if you just take it to the tens place, you get the same answer. And don't forget, if Q is less than K, it's going to move toward products. Before I wrap the video up, I just want to touch base a little bit on these relationships between equilibrium constants. Okay, so don't forget, K for the forward reaction, I'll call it K1. We know what that is. It's going to be products over the reactants. Now, what if I want you to write or give me the equilibrium constant for this reaction? Let's say I have a 2 and a 6 and a 4. My K prime is going to be equal to what? Remember, if I change the coefficients, if I multiply through by 2, you raise the equilibrium constant to that, whatever you multiply through by. If I multiply by 1/2, then I would take the square root. Okay, if I want the backward reaction, well, let's just leave it that way. I'll call it K3. The backward reaction would be 4NH3, and equilibrium was 2N2 plus 6H2. Well, that's just going to be 1 over K2. No biggie there. And the other one was if you had multiple reactions and you could add them all up, you would just have to multiply the equilibrium constants. So that's it, guys. Any questions for me on this stuff at all? Yeah. Now, next week we're going to get into acid-base equilibria, which is really interesting, and solubility equilibria. That'll take us about a week. Since we know equilibrium now, this is going to be pretty easy. I just have to explain about pH and stuff. Anyway, that'll come next week, and then right after that we're going to run into chemical kinetics, maybe a little electrochemistry, and we're done for the year.